Stacking semiconductors vertically isn't as simple as just pile them on top. The conditions needed to place real silicon above a finished circuit without damaging what's already below are finally starting to come together at the same time. Today, I want to talk about a piece of research that could be a significant step in that direction.
As always, I'll explain everything in the most simplified way possible. Even a middle schooler should be able to follow along. If you're a specialist watching, some parts may feel oversimplified, but I'd like to prioritize giving everyone the big picture first. We'll use the analogy of adding a new floor to a house while people are still living in it. So sit back and enjoy. Picture this. A construction crew is trying to add a second floor to a house, while the family inside is still living there. That first floor is fully furnished. People are going about their day. That first floor is your finished circuit layer. The transistors are already wired up and running. The challenge is, how do you build on top without disturbing the life below? The biggest constraint is heat. You can't bring in a blowtorch. There are people downstairs. If you go in with intense heat, the interior of the first floor gets damaged. It's the same in semiconductor manufacturing. Apply too much heat, and the transistors below drift out of spec, the copper wiring degrades, the insulating layers break down. The amount of heat you're still allowed to use after the lower circuit is finished, that's called the thermal budget. In the industry, the thermal budget after the first layer is complete is roughly 400 degrees Celsius. You have to add everything above within that limit. But here's the problem. Making high-quality silicon normally requires temperatures close to 1,000 degrees. You can't use strong heat, yet you want real building materials up there. This tension has been the industry's dilemma for years. The team behind today's research found two clever workarounds. The first, use ultra-thin, flexible sheets as the floor material. If you try to lay down a thick, rigid slab, it won't conform to the uneven surface below, and you get gaps, defects. But a paper-thin sheet drapes perfectly over any contour. No gaps, no defects. The second trick, don't do the high heat work on site at all. Normally, you'd need to process the materials in place, which would damage the floor below. Instead, they prefabricated the panels at the factory under whatever conditions they needed, then brought those finished panels to the site and clicked them into place at low temperature. Not just for one prototype house, for an entire housing development at near zero defect rates. This pre-built addition approach is the heart of what makes this research tick. Let me summarize the house addition stance. You need to build upward without disturbing the residents below, which means no high heat on site. The solution is ultra-thin panels, pre-made elsewhere, snapped in at low temperature, conforming perfectly to the existing surface. Simple in concept, but extremely hard to pull off at semiconductor scale. And honestly, my read on this semiconductor research maps almost exactly onto that house addition story. The team at the University of Illinois Urbana-Champaign did precisely this, at real silicon scale, on real wafers. Let me walk you through what they actually demonstrated. The silicone films they used were under 10 nanometers thick. These were lifted from a donor wafer and transferred onto a completed circuit below. For bonding, they used a roll laminator, essentially pressing the film down at temperatures below 200 degrees Celsius. The entire process stays under the 400-degree thermal budget. That ultra-thin sheet, snapped in at low temperature, exactly the concept from the analogy, done for real. For the transistors on the upper layers, they chose junctionless transistors, a type that has no source-drain junction in the traditional sense. Normally, forming source and drain requires high-temperature doping. To avoid that, they pre-doped the thin film uniformly at high concentration before transfer. And because the film is under 10 nanometers thin, the gate can still control the channel effectively, even without a junction. It's an elegant workaround. The demonstration didn't stop at a single transistor either. They built 3 stacked layers, each containing 625 transistors, connected vertically with metal interconnects. On top of that, they realized actual logic circuits, inverters, NAND, NOR gates, plus SRAM cells. Current density exceeded 650 microamps per micrometer. Yield, 98 to 100%. And all of this at 8-inch wafer scale. Now, let me give you the professional perspective. Research on stacking semiconductors vertically is not new. CFET, which stacks NFET and PFET vertically, has been around. There have also been many attempts using polysilicon, oxide semiconductors, carbon nanotubes, and 2D materials in the upper layers. So why is this one different? The real barrier has always been this. The upper floors were always built with cheaper, inferior materials. Everything that could be deposited at low enough temperatures, polysilicon, oxide semiconductors, performed worse than the silicon below. You went to the trouble of stacking in 3D, but the performance gap in the upper layer canceled out most of the benefit. That's the line nobody had crossed. What this research did was bring real silicon back to the upper layer. Not a compromised material, single crystal silicon, the mainstream of semiconductor manufacturing, placed on top without damaging what's below. That single point is what separates this from everything that came before.
What made it possible were those two design choices. Because the film is ultra-thin, it conforms to the surface below, and interface defects are minimized. And by choosing junctionless transistors, they eliminated the need for high-temperature doping on site entirely. Instead of solving a hard problem head-on, they switched to a fabrication method that doesn't need high temperatures in the first place. That's a smart pivot.
One application I find particularly interesting is SRAM. Today's SRAM uses 6 transistors arranged flat on a plane to store 1 bit of data. If you can split those 6 transistors across multiple layers, you shrink the footprint and, more importantly, you shorten the wiring distance between memory and logic. In AI chips, CPUs, and GPUs, that memory-to-logic distance directly impacts power consumption and performance. Bringing them closer vertically matters a lot. That said, to be honest, this doesn't mean the world's fastest CPUs will be 3-story buildings starting tomorrow. The transistors here are junctionless thin-film transistors, not FinFETs or GAA devices. The paper itself positions this technology as suited for research and low-volume prototyping. There are still real barriers, forming low-resistance contacts below 400 degrees, interlayer wiring resistance and reliability, and heat dissipation in a stacked structure. Multiple hurdles remain before mass production. Let me also consider what this means for Japan. First, to be clear, Japanese institutions were not involved in this research. Funding came from the U.S. National Science Foundation and Intel. That said, speaking generally, the process stack here, thin film deposition, low-temperature bonding, roll transfer, CMP, etching, overlaps heavily with areas where Japanese equipment and materials companies are strong. If the vertical stacking direction gains momentum, the importance of those tools and materials could grow further. That's how I read it. Let me pull it all together. What's impressive here isn't just that it's 3D. It's the combination. Single crystal silicon in the upper layers, a process temperature below 400 degrees, with bonding below 200 degrees, 3 stacked layers, working logic and SRAM circuits, demonstrated at 8-inch wafer scale. Each element existed in some form before, but showing all of them together at the same time, that's the combination that matters. That's all for today. I'll keep bringing you semiconductor news and analysis, so if you found this useful, please like, subscribe, and I'll see you in the next video. This has been Ty on Semiconductor News Decoded.